Hi, I'm Tim.
And I'm Ryan.
And today we're going to give a paired presentation about our new paper, an exact paired permutation test for structured test statistics. The first author, Ryan, couldn't be here today because he's off fixing compilation issues in his thesis as it's due in 2 weeks. So what this work is concerned with is probably the most important problem in all of NLP, which is whether or not my part-of-speech tagger is better than Ryan's part-of-speech tagger. And so the standard protocol for doing such a comparison is to take a bunch of input sentences and run them through my system, and to measure something like the accuracy, as that's unambiguous. And we'll do the same thing for Ryan, compute his accuracy, and then we'll just see whose is bigger, right? Ryan's is 0.3% bigger in this case, and so his is better. Or is it? Well, there's a little bit of nuance when comparing systems like this on a sample of input sentences, because Ryan might have just gotten lucky in the specific choice of input data that we used to compare our systems. And so often what is recommended that we do is we use something which quantifies the level of confidence we should have that Ryan's system is better than mine. And the specific technique that we're going to look at this paper is called the paired permutation test. And that's a method that'll tell us how confident we should be. And Ryan's going to tell you about that on the next pair of slides.
Thanks, Tim. And as Tim said, over the next pair of slides, I'm going to give you a crash course in paired permutation testing. This is going to set the stage for the algorithmic advance that really constitutes the meat of our paper. So the way that a paired permutation test works is that we first construct a distribution where the system's predictions are decoupled, that is to say, independent from the labels. And by labels, I mean whether the prediction was made by Tim's system or by mine. So you can see in this visual, Tim's system's predictions are encoded by a orange horizontal bar, and mine are encoded by a blue horizontal bar. And to get a distribution where the predictions are decoupled from the labels, we randomly swap the orange and the blue bars. We do this with uniform probability, and we end up with a distribution over all 2 to the n possible swappings, assuming there are n predictions. The question then becomes, when we want to decide whose part-of-speech tagging system is better, is we ask, how probable is it that we observe a pair of predictions where the difference in accuracy is as great as 0.3? So let's zoom in a bit more on the math behind this. So the way this looks in a more mathematical formulation is that we have a random variable that encodes the randomly swapped outputs, and we compute a function of that random variable, t, that encodes the test statistic, which is in this case the difference in accuracy. We then ask that the probability that that test statistic is greater than the observed effect, which is 0.3, and in the end, we end up with what's called a p-value. So the question we're asking, the computational question we're asking in this paper is, what is the most efficient way to compute this p-value? The simple way to compute it is to sum over all 2 to the n possible swaps. This is by construction an exponential time algorithm and completely unfeasible for any practical data set. A simple solution is to use a Monte Carlo approximation where we randomly sample swaps from big P and then we average the test statistics. However, this gives us an approximate p-value, which might not be what we want. We might want to know exactly what our p-value is for future replication issues. So what we present concretely in this work is an exact dynamic program that runs in polynomial time, as long as we assume a certain additive structure for t that Tim's going to tell you all about in the next slide.
Thanks, Ryan. So the specific family of test statistics that we're going to consider are what we called additively decomposable test statistics. And these are test statistics of the following form. We have a local test statistic, which only depends on a single input. And we will then just sum these local test statistics and apply an optional nonlinearity at the end. More formally, what this looks like is we have a test statistic that can be written in the following functional form. And what's nice about this family is that we have local probability mass functions, which are incredibly simple. For any given little n, there's only two possibilities of values that could possibly happen here. Either we stay or we swap at this specific input. And so there are two values depending, which are simply given by applying the g function for that given n on the swapped and unswapped input, output. And then given all of the local probability mass functions, we can get the global one, which is given by the sum of the random variables, g. And it turns out that the sum of independent random variables is simply the convolution of the local probability mass functions. And that's something that we can compute incredibly efficiently using a fast Fourier transform. And good implementations of fast Fourier transforms are already sitting in NumPy and SciPy, just waiting for you to use them. And that's what we did. The pseudocode over here gives you a sketch of what's going on. We compute the local PMFs. We evaluate our observed effect. We take the n-fold convolution of the local PMFs, and then we do a linear pass at the end to apply the nonlinearity h. And all right, that's great, but is it fast? Well, it turns out that it is. We compared our exact method against Monte Carlo, as well as a version of our method where we didn't use the fast Fourier transform. And what we found is that our system with the fast Fourier transform is incredibly fast. It runs faster than Monte Carlo with a really modest number of samples. In addition to being exact, it's faster. So you really ought to not use the Monte Carlo method, at least if you're comparing accuracy. Interestingly, if you don't have the fast Fourier transform, the scalability with respect to n is not as good. And so we found that this was pretty crucial. And so, I'm going to let Ryan tell you what we learned here. What did we learn, Ryan?
We learned when life gives you structure, you write a dynamic program and a paper about it.
Thanks, everybody. You can find code and the archive version of the paper at the following QR codes or links. Thank you.